Before we jump into problem 26, I want to dive into some facts and review what you already know. So let's look at these two very simple problems. If I asked you to solve this without even thinking, you would add 5 to both sides. And you've already programmed it in your brain that as long as you do the same operation to both sides, whether it's adding, subtracting, multiplying, or dividing, we keep the equation balanced. The left side and the right side receive the same operation. And so in this case, we're going to then divide by 2. And as long as you do the exact same operation to both sides, again, we keep the equation balanced. Here, we're multiplying by the reciprocal. And as long as you do the same thing to both sides, we keep the equation balanced. And we have 12 over 2, or x equals 6 again. So that's going to lead into what we're going to talk about next. So let's start off right now with looking at, let's go with something like this. Let's just remember really quick, what does this mean? So if I just gave you the expression log base 5 of 25 and I asked you to evaluate, what does that mean? Okay, that means 5 raised to what value equals 25. This is called logarithmic form. In my mind, I think of it like this. Base raised to the opposite value equals the number behind. And there I know that 5 squared is 25. Let's look at another one. So again, let's evaluate the second expression. So 2 raised to what power equals 16? 2 raised to what power equals 16? 2 times 2 is 4, times 2 is 8, times 2 again is 16. X equals 4. This third expression. So equals x is what I'm going to add behind it if we don't see this. Now the expression turns into an equation, allowing me to solve it. And think of this in the form, exponential form, base raised to the opposite equals the number behind the base. So how do I turn a 16 into a 4 using exponents? Well, I know that if I take the square root of 16, I end up with 4. And remember, the nth root is 2. So this value is 1/2. X equals 1/2. 1/2 is like taking the square root. Okay, now let's jump to what's called change of base formula. Even though this is the non-calculator portion, I need just to explain this to you. When you see this log button down here, this is log base 10. This is log base 10. So if I just gave this to you and I said, oh, evaluate this expression, we won't be able to do this in our head. We don't know what this is. Now, if I did this to you, we could do this one in your head. Log of 100. If you don't see a number underneath in the base position, it's a hidden 10. So 10 raised to what value equals 100? And the answer is 2. So whenever you see just this log is going to be base 10. Now, how do we change this when we don't have a base 10? So for instance, if this would have been log of 7, how do we do that? Now on the older calculators, we didn't have this option. So on your calculator, please hit math and go straight down until you get to log base. In this position, we're able to now put in a base of 10, it's a hidden 10, and the number behind it is 7. And we get this ugly irrational decimal that provides us with the exact answer. So years and years and years ago, we didn't have that on calculators. And so there was something called a change of base formula that allowed us to evaluate this expression using a calculator. And here's how it worked. You would take a log of whatever the back number is, which is 7, divided by a log of the base. In this case, it was a hidden 10. So I'm going to show you this right now, how they are equivalent. If I did right now, looking at this, if I hit math and went straight down to A, I could type in 10 for the base and 7 underneath. And we know that this is approximately 0.845. Now let me show you how it is equivalent to this. Using this change of base formula, it's not the larger or the smaller, it's the back number, log of the back number, divided by log of the base. So log of the back number, oh, I should put parentheses around this, log of the back number, divided by log of the base. And we get the exact same value. In fact, here's a really cool thing to understand. We can change the base, and it doesn't matter what positive integer I change it to. What positive integer I change it to, I'm going to show you how we continue to get this. So let's do this right now. Let's do this. We have math all the way down. Let's change it to 9. So I'm going to make this a 9. So log base 9 of 7 divided by log base 9 of 10. And what I'm demonstrating to you is I can change it as long as the base for both the top and the bottom remain the same, we're still going to get this exact same value. So let me even push it up to like 20. I want to show you how it does not matter. So let's go math all the way down, and let's make that base 20. The number in back is 7 for this particular one, divided by log all the way down, keeping the base exactly the same. The number behind this time is 10. We get the exact same value. So if I said to you, we don't have a lot of room here, log base 3 of 5. Now, in your mind, you're like, okay, can I do this mentally? 3 to the what equals 5? I don't know what that is. 3 to the first is 3, 3 to the second, 3 to the second is 9, 3 to the third, 20. I don't know exactly what that is. So what we would have done years ago is we'd use change a base formula if we had a calculator. Now, nowadays, you didn't have to use change a base. We could simply hit math, go all the way down again, and we have the option to do, we have a base here. So if I look back at this, we have a base of 3. The number behind is 5, and we can see that this is approximately 1.464, right? So we can see what that is, but what I do want to show you again is that we could change the bases here. So it could be like log base 13 of 5 divided by log base 13 of 3, and we should get that exact same answer. Last time it'd be just providing you with an example to prove this point. All right, so we've got this one divided by log base 13 of 3, and we should get the exact same answer, which we do. Now, how is that going to relate to what we're doing? Well, I've got one more thing to review with you before we get going on to problem number 26. And so here's what I want to review with you. Let's just rewrite these. So let's start with log base 7 of 4 divided by 1/3. How could I simplify that? Okay, so I'm taking log base 7 of 4 and I'm dividing it by 1/3. Remember, when we divide, we turn from division into multiplication. Now, where does plus 3 or 3 over 1 go? It goes in front. So this would be 3 times log base 7 of 4. And then also remember that when we condense things, any value out front becomes an exponent. So log base 7 of 4 to the third, log base 7, 4 times 4 is 16, 16 times 4 is 64. This is equivalent to this original expression. You do want to know these for what we're going to move into, so make sure you are writing these down. Let's look at another one. This next example is log base 7 of 8 divided by 3, so slightly different. So log base 7 of 8, I'm going to divide it by 3. Okay, I'm going to take log base 7 of 8 and I'm going to turn division to multiply, and I'm going to multiply by the reciprocal. So 1/3 is going to go in front. 1/3 times log base 7 of 8. Now that value or that coefficient in front is going to go right up top as an exponent. Log base 7 of 8 to the 1/3. What does this mean? We always are going to evaluate using the denominator of the exponential value. So what times itself, if we know it, what times itself 3 times gives us 8? 2 times 2 times 2. All right? So this is log base 7 of 2. This is equivalent to this. If I plug this into your calculator and I plug these into my calculator, I'd have the exact same value. All right, I think it's time to get started. So let's look right now at problem number 26. Problem number 26. Which of the following is not equivalent to log base 4 of 10? Well, let's start by trying. So I'm going to write it using the change of base formula first. So log of the back number divided by log of the base. And I'm going to, does anyone look exactly like this? Nope, nothing looks exactly like this. But remember, when I don't see a base, it can be any number. Like here, I don't see a base, so they had 10. They put 10 in. Here they must have put 2 in. Here they tried 8, and here they tried 16. When it says which of the following is not equivalent, that means 3 will work and 1 will not work. So I don't see a number. I'm going to start by trying A. I'm going to put a 10 in. Now, what does this mean? If I was just going to evaluate just the top and think of this as an expression, this means 10 raised to what value equals 10? 10 raised to what value equals, raised to what value equals 10? 10 to the first equals 10. So this top part is equivalent to 1. So I have 1 over log base 10 of 4. And you don't have to put, that's the only number you don't have to write as a base. When you don't see a base value there, it's a hidden 10. And we can see that this is equivalent to A. So that means A is equivalent to this original expression. And I'm looking for which one is not, and able to cancel out A. Now let's look at B. Let's look at B next. So looking at B, I can see they've now, instead of having a 10, so let's first do change of base. Log base 10 over log base 4. Give me 1 second. My kiddos are getting loud in the background.